Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz Hafizuddin bin Samsudin. My matrix number DE230120. So I will present about our project is process control system design for coconut oil purification. Including heating process optimization and temperature regulations. So our client is Musang King Sdn Bhd that be tendered by Dewey Hilltam Holdings. And our team is Group 1 Engineering Team, that is Basil, Muhammad Ismail Ghaffar, matrix number BE210005, and me, Muhammad Faiz Hafizuddin bin Samsudin, DE230120, and affiliation by University Tun Hussein of Malaysia. So, for the introduction and problem statement, precise temperature regulation is critical to preserving the quality and nutrient profile of coconut oil. The problem is industrial purification, poor thermal control leads to oil deterioration and nutrient loss and inconsistent physical properties. And our goal is the system must maintain a strict operating temperature of 150 degrees Celsius during the heating phase. And the challenges to the project is thermal systems are inherently slow with large time constant prone to steady state errors. So next is the performance specification and constraints. So our target set point is 150 degrees Celsius, for ambient is 27 degrees Celsius, and the overshoot is 6%. So the settling time is 1650 seconds, and actuation is 0 volt until 5 volts. So precision requirement is mean square error, MSE, that is must less than 1.5 times 10 power of -4 in steady state regions. So this is our workflow. Okay. So we starting from the process here. We identify FOPDT model, and then we tuning with using Ziegler-Nichols method, and then we simulate the closed loop system. And then we see the overshoot. Is it over the 6% or not? If it's over the 6%, then we need to tuning back the KP, the KI, the KD for the controller. If not, then we evaluate the response and implement anti-wind up, apply back calculation, and then evaluate response. And lastly is the report results. So this is the system modeling and parameter identification. So as we can see, the temperature in Celsius is here, is a y-axis, and then the time in second is the x-axis. So the time delay is 120 seconds, and the time constant here, and then the final is 1120 seconds. So the method is open loop stack response analysis. That is 5 volt input, and then the process gain is 41.2. And then the time constant is 100 seconds, and the time delay is 120 seconds. And then the system model as first order plus that time FPDT to capture thermal inertia. Transfer model, the transfer function model is this is our system gain 41.2, and then this is our dead time 120 seconds, and the time constant is 1000 seconds. So this mathematical represent the coconut oil heating dynamics. And then for the control strategy structure, controller strategy structure, this is a KP, KI, and KD. So for KP, immediate error correction, eliminate steady state error, and then overshoot improve tension is KD. And KI is the eliminate steady state error. So the design goals here is to balance fast rise time with stability to meet the less than 6% overshoot constraint. So that's all for me, and I will pass to my group members.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Basim Muhammad. My matrix is BE20005. For the result and discussion part, so as stated in the methodology, we are using FOBDT model. So here's the manual calculation for the transfer function parameter to get this important parameter, which is K and theta and tau. So using this graph to get the theta and tau and the gain. So after using the graph to get all this parameter, here's the transfer function. for the model. G is equal to 41.2 exponential of power of negative 120 second over 120 second 1000 second plus 1. So after getting these parameters, we use them for the tuning, and we use the Ziegler-Nichols method for designing the PID controller. So here's the calculation for the KB and KI, KD, and here is the all the system or the controller for the PID controller using Ziegler-Nichols method. So as shown in the MATLAB, here's the step, and this is the sum, and here's the PID controller that we design, and here the saturation, and this is the transfer function, and this is the transport delay, because in the transfer function we don't have the exponential part, the delay part for the theta, so we use it here, 120, and here the constant or the initial value that given in the question, which is 27 Celsius, and here the output. So this part is voting for to show the set point in the graph. I will show later in the graph. But first, for the PID, the parameter we get these are the parameter we get, but after showing the graph, it didn't give the correct value, so that's why we needed to tune using a Ziegler-Nichols method. Here is the parameter that we got. So after that, we manually tune the values to get the desired or the correct output response. So we use the manual fine tuning and the anti-wind-up logic. So we reduce the KB from 0.24 to 0.17, and the KI, which is the integral part, from 0.001 to 0.0005 to damp the aggression, because it gives aggression to the response. And then we also use the back calculation. So after putting this in the PID controller, as shown here, here are the new values after the manual tuning. So we show the result using the scope. So here's the output response, starting from 27 as the initial value. So it shows the final closed loop temperature response. So the horizontal line, which represent the set point, which is 150 degrees Celsius, where the curved line is showing the actual temperature response for the process, as you can see. So basically the response reaches the maximum temperature about 157, which is less than, if we calculate the overshot, we will get the overshot less than 6%, which is around 5%. So showing here in the slides, here is the peak value for the overshot. We will get 5%, and also for the steady state error or the MAC, we will get 0 error. So the set point shown here is the steady state, showing no error in the graph, as shown in the figure here. So here's the analysis for the results we got in the response. The peak value 157.5 Celsius, which gives the overshoot less than 6%, and the for steady state, zero error. And for the dynamics actuator using within 0 to 5 volt, which shows in the saturation from the lower limit to the 5 as given in the question. So and then there is no oscillation observed. So for the conclusion, the mission is accomplished perfectly because we get the output response within the desired value, which is exactly to 150 for the set point. So this is all for